Hey kids, now that you've seen the Eureka videos of the kinetic and potential energy, I would like to take a moment just to try to take a look at the connection between the two. We now know what potential energy is. It looks like we would be able to calculate that the potential energy was equal to the mass times the gravity times the height. So as long as an object has potential energy, as long as it has height, then it's going to have potential energy. And after an object starts to fall to the ground and it has a velocity, right before it hits, a final velocity there. I don't usually use the F, but I wanted to let you know what this was. If it has a final velocity just before it hits the ground, but you notice it has no height, we've recognized this as a kinetic energy that the object will have. And from the video, we were able to learn that it can be calculated as 1/2 times the mass times the final velocity, the velocity squared. So an object has kinetic energy as long as it's moving. Because right before it hits the ground, it has a final velocity, that means that it will have kinetic energy. What I would like to do is I would like to take a look at what I call LOL graphs. It's just a way that we can actually graph to see what is happening with the amount of energy that we have in an object. So I have these these three graphs down at the bottom, and we just want to plot how much potential and how much kinetic energy is in each one. So we have a potential and a kinetic, and likewise a potential and a kinetic. And so with my yellow marker here, I wanted to see just how much energy is in each one. So taking a look at the very first one, it has no height off of the ground. Right? It is resting right on the ground like that. And so because there's zero height, there's going to be zero potential. So I'll just have a little mark right there, kind of indicating that this right here is the zero. So we can see that I'm still recognizing potential, but it's obviously at zero. Likewise, because the object is not moving, it is sitting still on the ground, that means it will also have zero kinetic. So I can identify that the total mechanical energy of this object right now is zero in the very first case. In the second case, though, I can clearly see that there's a height, and so there will be an amount of potential energy. But again, this is just kind of resting off of the ground. It's starting from rest, and so likewise there's going to be zero kinetic energy. Where the O comes in is actually just an indicator of whether or not work was done on the system. In order to get energy into an object, we have to actually do work on that object. I needed to have physically lifted this object upwards, and so I needed to apply a force, some kind of an applied force, that was at least as equal to the force of gravity, so that it would actually start to move upwards. We could say that the minimum force required in order to do work is got to be equal to the force of gravity. But then we moved it up a displacement, a certain height that we recognize here as h. Sometimes I will call that delta y because that's the same thing that we've used as height. So because work was done in order to give the object potential energy, before we had no energy, afterwards, we obviously had energy, so that means that work had to have been done. So in other words, the way we draw this is we draw an arrow going into the O, and then we say inside the O, we would indicate plus W. So that means that work was done. Positive work was done in order to give energy to the object. Now, if I lowered this object to the ground, if I physically grabbed the object and I then would lower it. So here's me grabbing the object, and I would actually lower it down to the ground like that. Then we could see that I was taking energy away from the object, and that's when we would put negative W in that circle, or negative work was done because you were removing it. But keeping this where it was, we'll just keep that in play. And I can see that there is potential now and no kinetic. Now to go to the third picture though, I can see that I didn't apply a force to it. So there wasn't any work done. And so what I would just say is, oops, my mistake. I would say 0W to indicate that no work was done. So no energy was taken away from the system. Because energy wasn't taken away from the system, that means that the total mechanical energy must not have changed. So to take a look here, I obviously have zero potential because it is literally just about to hit the ground. However, all of the energy that I had before, every single shred of it, every piece of energy that I had that was potential, must now be converted into kinetic energy because it's just about to hit the ground. So this is a way that if I'm able to go ahead and calculate how much potential an object has, I could figure that just before it hits the ground, it will have that same amount of energy, but in kinetic form. And with that mass, I can figure out just how fast an object will be right before it hits the ground. This is another way that I would be able to solve an old kinematics problem that we have seen before. How fast will an object be moving right before it hits the ground? But I could solve it now in terms of energy. As long as I could establish that no work was done on the object between when it was at rest and then it was freely moving through the air, I could see that all of that energy would be transferred from potential to kinetic. All right, I hope that this clears a little bit of a connection between work, potential energy, and kinetic energy, and you can see where all three of these things can be connected to one another and how they tend to interact. This is sometimes called the work-energy theorem, and we're going to be spending a lot more time working with the work-energy theorem. All right, kids, thanks for watching this video, and I hope you enjoy your weekend. See you on Monday.